Welcome everyone. My name is Elif Yanık and I'm a chemical engineer who graduated from Ankara University. Before starting, I would like to express my gratitude to each member of the host committee for their effort in preparing this online conference. Today, I will be presenting my research on the fast and complete destruction of acid Fuchsin dye from water by Electro-Fenton based processes. This study focuses on investigating the removal efficiencies of advanced oxidation processes applied to dye-contaminated water. In this presentation, I will briefly introduce the treatment principles examined in the study and then move on to the experimental setup, results, discussion, and concluding remarks. Globally, approximately 50% of dyes used in industrial applications are discharged directly into water bodies as wastewater. The textile industry is one of the most water-intensive sectors, and the dyes used in this industry represents a major source of aquatic pollution. Acid Fuchsin, the selected model contaminant in this study, is widely used in the textile industry and in laboratories and contributes substantially to aquatic pollution. Textile dyes typically exhibit high non-biodegradability and persistence. They inhibit plant growth by interfering with photosynthesis and elevate COD and BOD levels. In addition, many dyes are toxic and some possess mutagenic or carcinogenic characteristics. Due to their high stability and solubility, many dyes cannot be effectively treated using conventional methods. These methods often fail to fully degrade the dye, generate toxic intermediates, or become economically impractical. In the Electro-Fenton process, hydrogen peroxide is electrogenerated through the reduction of dissolved oxygen at the cathode, while ferrocians are continuously regenerated, sustaining hydroxy radical formation. When anodes with a high oxygen evolution over potential, such as boron-doped diamonds, are used, additional hydroxy radicals are produced through water oxidation at the anode surface. This further enhances the oxidation capacity by introducing anodic oxidation pathways. In the photoelectro-Fenton process, UVA and UVC irradiation accelerate ferric to ferrocyan cycling via photoreduction, while also generating additional hydroxy radicals through the photolysis of hydrogen peroxide and organic intermediates. However, the requirement for low pH operation, the need for additional physical treatment steps, and the disposal of soluble iron species limit the scalability of homogeneous photoelectro-Fenton systems. To overcome these limitations, heterogeneous systems have been developed. Heterogeneous Electro-Fenton employs insoluble iron-based catalysts and offers several advantages, including operation over a wider pH range, easy separation, and reusability of catalyst. Magnetite, owing to its mixed valence ferric ferrous structure and magnetic separability, is a particularly attractive catalyst for activating hydrogen peroxide. Heterogeneous photoelectro-Fenton combines solid catalyst with both electrochemical and photonic activation. In these systems, hydrogen peroxide generation, regeneration of surface ferrocides, and photonic activation under UV irradiation act cooperatively, producing high hydroxy radical fluxes. This slide shows the experimental setup used throughout the study. For homogeneous Fenton-based systems, 0.1 millimolar iron 2-sulfate heptahydrate was introduced as the catalyst prior to experimental initiation. For photoelectro-Fenton experiments, UVA at 365 nanometers and UVC at 254 nanometers were used as external irradiation sources. For heterogeneous systems, 0.1 grams per liter of magnetite nanoparticles were used. The catalyst was synthesized using the co-precipitation method. All experiments were conducted in a 250 ml glass reactor containing 200 ml of 0.05 millimolar acid Fuchsin solution and 50 millimolar sodium sulfate as a supporting electrolyte. The pH was adjusted to 3 using dilute sodium hydroxide and sulfuric acid solutions. A BDD anode and a carbon felt cathode were arranged in a parallel configuration and connected to a direct current power supply. The experiments were performed under constant current conditions ranging from 50 to 500 mA with continuous magnetic steering to ensure homogeneity. Compressed air was introduced 5 minutes prior to each experiment and maintained throughout to provide oxygen gas, and periodic samples were collected for color and COD analysis. Here, figure 11 shows the effect of current intensity on acid Fuchsin degradation using Electro-Fenton. Complete degradation was achieved in all cases, with the fastest removal occurring at 18 minutes under 100 mA. As figure 12 indicates, the fastest and complete COD removal was achieved at 36 minutes under 100 mA. Figure 13 and 14 show the degradation and mineralization results for Electro-Fenton. The process achieved complete degradation at 18 minutes and complete mineralization at 60 minutes under 100 mA. Figures 15 and 16 illustrate the heterogeneous Electro-Fenton performance. Complete color removal occurred at 24 minutes at 100 mA, and mineralization increased steadily with current, and the fastest complete COD removal occurred at 36 minutes at 500 mA. The findings of the heterogeneous Electro-Fenton method are illustrated in figure 17 and 18. Complete degradation was achieved at 18 minutes under 100 mA. Complete mineralization was obtained within 36 minutes under 500 mA and within 60 minutes under 100 mA respectively. Color removal increased as the current was raised from 50 to 100 mA due to enhanced hydroxy radical generation. However, higher current values did not produce further improvements. With this in mind, we now examine mineralization rates across all treatment methods. The effect of current on mineralization varied among the methods. While 50 mA remained insufficient, increasing the current beyond 100 mA did not consistently yield higher COD removal. To clarify these results, we examine the possible underlying mechanisms. Removal efficiencies increased when the applied current was raised from 50 to 100 mA, primarily due to enhanced formation of hydroxy radicals. BDD anode promotes the generation of large quantities of heterogeneously formed hydroxy radicals, while the increased rate of electrogenerated hydrogen peroxide at the cathode simultaneously enhances the formation of homogeneously hydroxy radicals in the bulk solution. In addition, the intensified anodic oxidation creates a synergistic effect with catalyst regeneration at the cathode, collectively supporting higher radical production. In homogeneous systems, ferric ions are reduced to ferrous ions via cathodic reduction, whereas in heterogeneous systems, surface ferric sites on the catalysts are reduced to ferrous sites, further sustaining the Fenton reaction cycle. Nevertheless, increasing the applied current beyond 100 mA did not result in considerable further improvements. This is due to competing side reactions such as hydrogen gas evolution at the cathode, reduction of hydrogen peroxide, and oxygen evolution reactions occurring in the anode. Furthermore, at currents above the optimum value, hydroxy radical scavenging becomes significant. Under these conditions, when side reactions begin to dominate, hydroxy radicals may also react with hydrogen peroxide to form hydroperoxide radicals, which exhibit substantially lower oxidative reactivity, thereby diminishing overall treatment performance. In conclusion, Table 1 summarizes the comparative results, which indicate that all processes achieved effective degradation and mineralization of acid Fuchsin. However, when comparing overall performance of the methods, Electro-Fenton exhibited the highest performance, followed by heterogeneous Electro-Fenton and Electro-Fenton processes, which outperforms heterogeneous Electro-Fenton. These are the references used throughout the study. Thank you for your time and attention. I am happy to answer any questions from the audience.